In this lesson, we're going to cover absolute convergence and the ratio and root tests. Our first definition, it says a series, and we have a sub n, is called absolutely convergent if the series of absolute values is convergent. This example says consider the series. So we have negative 1 to the n minus 1 over n squared. Because of this part up here, the series is alternating. So next, if we take the absolute value of this series, we're going to get all positive terms. And then we can look at this new series, which can be written as sigma of 1 over n squared. So now when looking at this series is in the p series form, where p is equal to 2 and 2 is greater than 1, therefore this series is convergent. So if we go back to this definition, since the series of absolute values, so since this series is convergent, we would then say that this original series is absolutely convergent. This note says if your series a sub n is a series of positive terms, then when you take the absolute value of it, you still get out the same series. So absolute convergence is the same as convergence. Our next definition says a series a sub n is called conditionally convergent if it is convergent, but it's not absolutely convergent. So here's an example that shows conditionally convergent. So we're going to consider the series. We have negative 1 to the n minus 1 over n. Again, this is an alternating series. It goes 1, then negative 1/2, then positive 1/3, negative 1/4. So if we look at the alternating series test for this series, b sub n is 1 over n, and these terms are decreasing. So the first condition is satisfied. And then if we take the limit as n goes to infinity of 1 over n, we'll get 0. So the second condition is also satisfied. So therefore, by the alternating series test, this series converges. So now we're going to look at the absolute value of the series. So that means that we have just the series 1 over n, which equals 1 plus 1/2 plus 1/3, and so on. And you're probably noticing this is a harmonic series, and a harmonic series diverges. So I just wrote that out, that this series diverges. So again, what happened is we have our original series converges by the alternating series test, but because the absolute value of the series doesn't also converge, we say that this original series is conditionally convergent. This theorem says if a series a sub n is absolutely convergent, then it is convergent. Next, we have the ratio test. To apply the ratio test, we take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. We evaluate this and we get out L. If L is less than 1, then the series a sub n is absolutely convergent and therefore convergent. If when we evaluate the same limit and we get out L but L is greater than 1, or when we evaluate we get out infinity, then the series a sub n is divergent. And then last, we evaluate the same limit if it equals 1. The ratio test is inconclusive. Therefore, we try another test, except we're not going to use the root test, which is what we're going to talk about later in the chapter. This example says determine if the series is absolutely convergent, conditionally convergent, or divergent. So for part A, we have sigma of negative 1 to the n times n to the third over e to the n. So again, this is a sub n, and I have that written right here. And then we're going to identify a sub n plus 1. So what that means is anywhere you see an n, we're going to replace it with n plus 1. So again, we had n here, here, and here. And in all of those, we have now n plus 1, n plus 1, and n plus 1. Okay, to set up the ratio test, we do the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. So I have a sub n plus 1 written down. And next, we're going to divide by a sub n. But dividing by a sub n is the same as multiplying by its reciprocal. All right, so we have this set up. So now we're going to simplify. I'm going to start with this e to the n plus 1. So e to the n plus 1 is the same as e to the n times e to the 1. And by breaking this up like this, you can see that this e to the n will cancel with this one. And then we just have e to the 1 in the denominator. The same thing happens for this negative 1 to the n plus 1 and this negative 1 to the n. If we break this up, it's going to be negative 1 to the n times negative 1 to the 1. So the negative 1 to the n is going to cancel with this one. And then all that you have left is negative 1 to the 1. So at this point, we're taking the absolute value of this expression. So a couple of things are happening. The absolute value of negative 1 is positive 1. The absolute value of this 1 over e is 1 over e. And then it says n is getting larger and larger in the positive direction. So that means we're plugging in 1 for n, then 2, then 3, and 4, and so on. So if you take the absolute value of those numbers, you'll just get out the same thing because they're positive. So when we take the absolute value of this expression, it's just going to be the exact same expression, except there won't be this negative 1 here. At the same time, I'm going to bring this 1 over e to the front, And then I'm going to rewrite this. It says n plus 1 quantity cubed, and this is n cubed. So I just rewrote it as n plus 1 over n all to the third power. To evaluate this, we have a composition of functions. So I'm going to bring the outside function, which is quantity cubed, to the outside, and then we're going to take the limit of the inside function. So at this point, there's a couple of ways to finish this. We have the limit as n goes to infinity of this rational function. We could split this up and say it's 1 plus 1 over n. We could evaluate it that way. Or we could say that the degree on top and the degree on the bottom are the same. So this infinite limit is equal to the ratio of their leading coefficients, which is 1 over 1. Either way, this limit equals 1. So then 1 cubed is 1. 1 times 1 over e is 1 over e. So this is our value for L. Again, the value you get, you're checking these three cases. Either it's going to be less than 1, or our second case is it's greater than 1 or equal to infinity, or the third option is it's equal to 1. So we got 1 over e, so that's less than 1. And it says the series is then absolutely convergent and therefore convergent. So I wrote it out, therefore by the ratio test, the series is absolutely convergent. For this example, we have the series -1 to the n plus 1 over the fourth root of n. So our a sub n is going to be this formula. And then for a sub n plus 1, we're going to plug in n plus 1 for this n, and then also for this one. When we plug in n plus 1 for n, it's going to be n plus 1 plus 1. So that makes n plus 2. And then for this n, we just put n plus 1. To set up the ratio test, we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, so here's our limit, the absolute value, and this is our a sub n plus 1. Now we're going to divide by a sub n, which is the same as multiplying by its reciprocal. Okay, so at this point right here, we have -1 to the n plus 2. This is -1 to the n plus 1. So we could split this up to n plus 1 plus 1. And then we could even split this further and go -1 to the n plus 1 times -1 to the 1. -1 to the n plus 1 would cancel with the -1 to the n plus 1 up here, and it would just leave -1 to the 1. But ultimately, we're going to take the absolute value of this whole expression, and that will take care of that -1. As n gets larger and larger in the positive direction, remember you're plugging in positive values to these two expressions, and the absolute value of a positive value is going to be just that value. So when all of that happens, we end up getting the limit as n goes to infinity of the fourth root of n divided by the fourth root of n plus 1. Since the numerator and denominator are both underneath the fourth root, we can rewrite our fraction. So now we have just the fourth root of n over n plus 1. So at this point, we have a composition of functions. So we're going to pull the outer function to the outside and take the limit of the inside function. And to evaluate our infinite limit, we have a rational function. The degree of the top and the bottom is the same. So this limit equals the ratio of their leading coefficients, which is 1 over 1 or just 1. Okay, so we got +1. According to the ratio test, if you take the limit and you get 1, it says the ratio test is inconclusive. And I just wrote it out, the ratio test is inconclusive. So what we're going to do is we're going to go back to this original series, and you're probably noticing that it's an alternating series. So we're going to apply the alternating series test to first determine whether or not this is convergent or divergent. Okay, so your alternating series test, first you identify b sub n. So b sub n is the non-alternating part, so it's 1 over the fourth root of n. As we plug in 1, then 2, then 3, and so on, you can see that the terms are going to decrease. So b sub n is decreasing. Okay, next we take the limit as n goes to infinity of b sub n. As you plug in larger and larger values, this fraction is going to go to 0. So since the two conditions are satisfied, the original alternating series converges by the alternating series test. So I wrote that out, therefore by the alternating series test, our series converges. So now that we know that the series converges, next we want to check the absolute value of the series. So when checking the series of absolute values, we take the absolute value of this series. And when we take the absolute value of this series, basically it takes this -1 to the n plus 1, and the absolute value of that numerator just becomes 1. In the denominator, when you take the absolute value of positive terms, you just get out those same terms. So we have sigma 1 over, and it's the fourth root of n, but I'm going to rewrite this as n to the 1/4. So now we can see that this is of p-series form, where p equals 1/4, and 1/4 is less than or equal to 1. So therefore, the series of absolute values diverges. Okay, so finally, since the original series converges, but the series of its absolute values diverges, we can say that the original series is conditionally convergent. So again, therefore, we can conclude that the original series is conditionally convergent. So I just want to reiterate for any future problems that you come across, we first took this alternating series, we applied the ratio test. If you get 1, then the ratio test is inconclusive. And again, since this is an alternating series, then we applied the alternating series test. So we got that it converged. At this point, we checked the series of absolute values and we got divergent. But in the future, if you get convergent, then you would say that the original series is absolutely convergent. For part C, we have sigma n squared over 2 to the n. And then I have a note, it says since the series has positive terms, when you take the absolute value of positive terms, you just get out the same terms. So therefore, absolute convergence would be the same as convergence. All right, so to apply the ratio test, first we want to identify a sub n and a sub n plus 1. So here's our a sub n, and then next we're going to find a sub n plus 1, and now we'll set up the ratio test. Okay, so for our ratio test, we have the limit as n goes to infinity, the absolute value, and then we have a sub n plus 1 divided by a sub n, which again we did times by the reciprocal of a sub n. Next, we want to simplify this. We have 2 to the n plus 1, and then we have 2 to the n. Remember this, you can rewrite it as 2 to the n times 2 to the 1. So then the 2 to the n's will cancel. And don't forget, you still have a 2 to the 1 right here. Next, when we take the absolute value of this whole entire expression, n is going in the positive direction, so the absolute value of a positive is just that same expression. So I'm going to bring this 2 to the front, and then all that we have left in here is just the n plus 1 squared over n squared. Because both the numerator and denominator are raised to the power of 2, I just rewrote it as one big fraction, all to the power of 2. This is the limit of a composition, so I'm going to bring the outside function to the outside of the limit. And again, this is a rational function where the degree on top and bottom are the same. So the infinite limit is equal to the ratio of their leading coefficients. So that's going to be equal to 1 over 1 or just 1. So we end up getting 1/2, and 1/2 is less than 1. Therefore, by the ratio test, the original series is absolutely convergent. And again, because the original series consists of positive terms, being absolutely convergent is the same as being just convergent. For part D, we have the series e to the negative n times n factorial. And I have a note, since this series has positive terms, when we take the absolute value of the terms, we're going to get out the same terms. Therefore, absolute convergence would be the same as convergence. So again, to apply the ratio test, we're going to identify a sub n and a sub n plus 1. So a sub n is the original formula. We have e to the negative n factorial. And then a sub n plus 1 means we're plugging in n plus 1 here and here. So we have e to the negative, and then I put parentheses n plus 1, and then we have n plus 1 factorial. So let's go ahead and set up our ratio test. So we do limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. And I'm going to distribute this negative right here. All right, so we have it set up. This is our a sub n plus 1, and this is our a sub n. So similar to our previous problems, we can split this up to e to the negative n times e to the negative 1. And when we do that, these e to the negative n's will cancel. But remember, you still have e to the negative 1 up here. So I'm going to move that e to the negative 1 to the denominator. So again, this e to the negative 1, I moved it to the denominator, so you just have e to the 1 on the bottom. And then I rewrote this n plus 1 factorial and then n factorial. And we got rid of the absolute value because these were all positive terms. So the absolute value of a positive is just a positive. Okay, so at this point, I'm going to bring this e to the front as 1 over e. And then the next thing I'm going to do is this n plus 1 factorial. Remember, the way factorial works is if you have 4 factorial, it equals 4 times 3 times 2 times 1. So whatever we have originally that has the factorial, you start with that, and then you subtract 1 and write it down, then you subtract 1 and write it down, and it goes all the way down to 1. So we're going to use that same concept to rewrite this. So to evaluate this factorial expression, first you start with n plus 1, and then to get the next one, you take n plus 1 and you subtract 1. So that makes n. I could have kept going. I could have said n, and then we could have times by, and then n minus 1, and then we could times by n minus 2. But in the denominator, we have n factorial. And so that's why I stopped here, so that they will cancel. Okay, so I just want to show this with numbers also, just to make sure it's making sense. If we have 5 factorial over 4 factorial, we agree that 5 factorial can be written as 5 times 4 times 3 times 2 times 1. And again, we could write it out that way, or we can notice that this right here is the same as 4 factorial. So instead of writing 4, 3, 2, 1, we can write 4 factorial like that. And by writing it like this, you can easily see that these cancel out. So we're just left with this 5. So to apply this to this situation, Again, we started with n plus 1 factorial, so we wrote n plus 1 times, and then we stopped at n factorial because that's what's in the denominator. And again, the point of this is so that these will cancel. So now all that we have left is 1 over e times the limit as n goes to infinity of n plus 1. So at this point, n is getting larger and larger. This expression is going to grow without bound. And so this whole expression is going to equal infinity. And since we got infinity, by the ratio test, the original series diverges. So I wrote it out, therefore by the ratio test, the original series is divergent. Our next definition is the root test. We have 3 different cases similar to the ratio test. What we do is we take the limit as n goes to infinity of the nth root of the absolute value of a sub n. And then when we evaluate this, we'll get L. If L is less than 1, then the original series is absolutely convergent and therefore convergent. Our next case, if we take the limit and evaluate it and we get a number greater than 1 or we get infinity, then the series is divergent. And then finally, if when you evaluate your limit and you get 1, the root test is inconclusive, therefore try another test except don't try the ratio test. This example says use the root test to determine whether the series is convergent or divergent. For part A, we have our series is negative 1 to the n over the natural log of n raised to the power of n. Okay, so to start the root test, we take the limit as n goes to infinity, and then we have the nth root of the absolute value, and then I took this expression and wrote it in right here. So first, the absolute value of this fraction. Remember when you're plugging in 1, then 2, then 3, this is going to alternate from positive to negative. And then when you take the absolute value of a positive, you'll get a positive, and the absolute value of a negative will also be a positive. So then this becomes the limit as n goes to infinity of the nth root of 1 over natural log of n raised to the n. So next we're going to split up the fraction. We're going to go the nth root of 1 divided by the nth root of this denominator. So now if you take the nth root of 1, you're just going to get 1, and the nth root and this power of n are going to cancel out. So we get the limit as n goes to infinity of 1 over natural log of n. So as n gets larger and larger, this fraction is going to go to 0. All right, so we get 0, and we're going to go back up and look at the root test. And you can see from your 3 different cases, 0 is going to be less than 1. Therefore, the original series is absolutely convergent and therefore convergent. So I wrote it out, therefore by the root test, the series is absolutely convergent. For part B, we have the series negative 9 to the n, all divided by n times 10 to the n plus 1. So we're going to set up the root test. We're going to take the limit as n goes to infinity of the nth root of the absolute value of this expression. So before I plug this expression in, I want to rewrite something real quick. So this is our a sub n. And then right here we have negative 9 raised to the power of n. So I'm going to take negative 9 and rewrite it as negative 1 times 9. And then next I'm going to split this up. So I'm going to rewrite it as negative 1 to the n times 9 to the n. And that's what I'm going to write down here. So some people think of when you go from here to here, they use the phrase shower the power, where right now both of these numbers have a power of 1. So you shower the power, meaning you multiply the 1 by n on both of them. So then you can rewrite it as negative 1 to the n times 9 to the n. So by doing that step first, it works out kind of nice because now when we take the absolute value of this fraction, the absolute value of the negative 1 to the n, that part just becomes positive. And then we're plugging in positive values for all of these n's, so the absolute value of this expression is just going to be itself. So next what I'm going to do is this says the nth root. I'm going to rewrite this as all to the power of 1 over n. And then for this n, I wrote in a little 1 because its exponent is 1. And again, this is kind of like a big shower the power problem. We have powers to powers, so we multiply. So again, when you have 9 to the n and it's raised to the 1 over n, we multiply n times 1 over n, and that just makes 1. So we end up getting 9 to the 1. So next, when we shower the power down here, we have 1 times 1 over n, so that makes n to the 1 over n. And then on this 10, we have n plus 1, so we multiply the 1 over n to both terms. So we get 10 to the 1 plus 1 over n. So now we're going to take the limit of the top and the limit of the bottom. Since this is a constant, the limit of the top is just that constant. When we take the limit of the denominator, we have a product. So we do the limit of the first times the limit of the next thing. This is looking a little crazy, but at this point, n gets larger and larger, so we work with this exponent first. So the limit as n gets larger and larger, this fraction is going to go to 0. And then n to the 0 power is just 1. And then over here, as n gets larger and larger, this is going to go to 0. So we have 1 plus 0 just makes 1, so we have 10 to the 1, or just 10. So now at this point we have 9 over 1 times 10, so that simplifies to 9/10. And according to the root test, 9/10 is less than 1, therefore the series is absolutely convergent and therefore convergent. So I wrote it out, therefore by the root test, the series is absolutely convergent. Alright guys, thanks so much for watching, and please subscribe to my YouTube channel and hit the like button. Alright, take care.